Okay, so we're going to start by talking about functions in this section. And just to kind of point out, functions are probably the most fundamentally important idea that you're going to see pretty much in almost every math class. So let's start off with defining what a function is. And you may have defined functions before. You may have a good idea as to what a function is. And you'll notice that we will make references to functions or the definition of a function quite a bit in this class. So we can say, look, a function is a rule that assigns each input. And this input that we talk about, I think what you're usually used to is what usually x is your input. But you'll notice, especially when you get into calculus, it doesn't necessarily always have to be x. So this is in a set A. So I'm just calling the set of all numbers that are in my input, I'm calling that set A. Exactly one output, and usually the output we call y or f of x. Now here's the key word. If you look at this, if I were to put emphasis on one word here, it would be this word. So let's underline that, because see, here's what we know. This is a function is a rule that assigns to each input in a set A exactly one output. So in other words, what are we saying? It would be impossible to plug in one input and get two different outputs. That's going to be impossible. Okay, so each input should only take me to one and only one output. If it takes me to more than one output, then that means it's not a function. Okay, so just keep that in mind. So then let's kind of define some more things here. So the set of all inputs of a function f of x is called the domain, which I'm sure you talked about this quite a bit last year, right? So all the inputs represent the domain. And of course, what are the outputs going to be? I'm sure we all know that as well. And the set of all outputs is called the range. Okay, so one other comment, I actually forgot to put something over here in the definition. Exactly one output in a set B, because what we know is that our output is going to be also a set of values. So to stay consistent with set A as my inputs, then the set B will be the outputs. It's just a list of numbers, right? When we say a set, it's a list of numbers. Okay, so let's kind of keep going with the description here or definitions. The variable that represents the domain is known as the independent variable. Let's also underline that because that's a definition that we need to know. And the variable that representing, so that's representing the range, is the dependent variable. So if you think about it, all we're doing is we're saying, look, these inputs that we talk about, they're known as the domain. And that input variable that we call it, that represents the domain, we could also call that as the independent variable, which makes sense. The name should make sense, because when we call it an independent variable, that means you can plug in anything into your function, whatever the input is. The dependent, see, why is the output the dependent? Because it depends on what you initially plug in. So your y values or your range, those variables are known as the dependent variable. So this is just some terminology you need to make sure to know. So if I ever say, hey, where's my independent variable, you're looking for the variable that represents the domain. And if I'd say, hey, what's the dependent variable, you're looking for the variable that represents the range, or its output, basically. Okay, so one other thing that I always like to do is, which this is kind of like a classic picture I always use when we try to describe visually what functions are. So don't worry about these blobs. So this is set A. So based on our definition here, now I'm going to give you a visual description of this. A is my domain. So what does that mean? This is a set and it's filled with some values. So let's say I put x sub 1, x sub 2, and x sub 3. So what am I saying? In this blob right here, which represents my set A, I have how many entries? I have 3 entries. So if A represents my domain, in this case I have 3 elements in my domain. So the domain of this function that I'm describing is x sub 1, x sub 2, and x sub 3. And then we can draw another blob, right? And we can call this region set B, which let's call this y sub 1, y sub 2, y sub 3. So the elements in set B are y sub 1, y sub 2, and y sub 3. So then the rule of the function is what? Or if we do have a function, the rule says the following. If I'm going from here to here, this is f. So what is it that we notice? We would say x sub 1. Let's say the rule I tell you, we plug in x sub 1 and x sub 1 takes us to y sub 2. So right, this is my input, my output is y sub 2. And let's say if I plug in x sub 2, my output is y sub 1. So far, is this a function? If you think about it, each input has taken me to one and only one output, which that's fine. Now, what if I do this? X sub 3 goes to y sub 2. Now, question for you guys. Is this a function, this picture that I've drawn, yes or no? So if you said it's not a function, let's be careful. I could see why you'd say it's not a function, because look, I have 2 different inputs that take me to the same output, which that's fine. There's nothing wrong with that. When would this not be a function? If, let's say, x sub 1 took me to y sub 2 and y sub 1, for example. So as long as each input takes me to only one output, then it follows the rule of a function. So this is in fact a function. So one comment I want to make here, which is kind of, I already made a mention here, but let's put it in our notes because I feel like it's important. A function may have 2 different inputs produce the same output, which is kind of like what happened here, right? X sub 1 and x sub 3 took me to the same output, which is y sub 2. However, but cannot have one input produce 2 different outputs. Okay, so I hope this picture didn't confuse you, right? Because all I'm really doing is I'm just trying to visually show you that, hey, this input took me there, right? So there's a rule that the function follows. I haven't given you the rule. All I'm just showing you is that this is visually. So for example, if I were to give you another visual example here, if I said, look, this is my input, this is my output. Let's pretend that x sub 1 takes me to something like this. X sub 1 does this and does that. So what do we notice? This is a rule, but what happens? What's the problem? X sub 1 takes me to 2 different outputs. So clearly this picture shows some relation that's not a function. Okay, so we're going to notice later on that for things being functions, they're going to be important. It's going to be important to make sure certain things are functions. Okay, so here's a visual of something that's not a function. But in the future, if you're ever asked to check to see if something is a function or not, you want to check, hey, is it possible for me to put in one input where it gives me two different outputs? If that's the case, then it's not a function. If that's not the case, then it is a function. So now let's talk about evaluating functions. So, and you've probably done plenty of this last year. I think if there's one thing that you did lots of is evaluating functions. So the idea here is when we're asked to evaluate functions, we will be given specific inputs and in order to find its corresponding output. Okay, so let's look at our first example where we're literally going to be evaluating. So we could say given f of x equals to negative 2x squared plus 2x minus 2, we'll say evaluate a f of negative 2, b f of 1, and c f of 0. So I would recommend that, you know, if you can do these all by yourself, pause the video, do these by yourself, and then press play. But this shouldn't be anything new to you. So f of negative 2 will literally just be, what am I doing here? I'm just replacing negative 2 in for x, and I get basically, this becomes 4 times negative 2, which is negative 8. 2 times negative 2 is negative 4, minus 2, which ends up being negative 14. Right? So f of 1, same idea. So I'm just going to give you the answer to these, and then if you want to, you should just do the steps to verify them. If I plug in 1, I get negative 2. Okay? And then if I plug in 0, I also get negative 2. So notice how obviously this is a function, and is it a concern to us that we have two different inputs taking us to the same output? Absolutely not. I'm not concerned about that. I would be concerned if I plugged in 1 into x and I got two different values, right? If, like, let's say f of 1 is negative 2 and positive 2, for instance, then that would no longer be a function, okay? But this is in fact a function. So let's get into the next concept, which you may not have seen last year, which has to do with piecewise functions. Okay, so piecewise functions, the way I think about this is they're kind of like a collection of functions. Okay, so nothing difficult, is just you're going to have different functions defined on specific domain values, and then they're going to be placed together or grouped together. So piecewise functions consists of multiple functions defined on different parts of its domain. Okay, so one comment I want to make, note, domain values will never overlap. And the reason being is we don't want the domain values to overlap because we want it to stay a function. So let's just jump into our first example, or our next example, where you'll see how a piecewise function looks. So one comment I want to make is you're just going to see a bunch of functions grouped together and they represent one big main function. So we would say, for example, 2, for the piecewise function which is defined as g of x equals, and then we put a brace. Now look, why is this a piecewise? Because I'm going to write multiple functions here. So g is a function of its own, and the way it's defined is the following: x squared if x is less than 0. So what is this saying? When x is less than 0, you're going to refer to this function. Okay? Now, if x is greater than or equal to 0, less than 2, we're going to use 1. So now what is it saying? When my x values are between 0 and 2, my function that I'm going to focus on is just g of x equals to 1. And then lastly, x cubed if x is greater than 2. So hopefully you see where you see where it gets the name piecewise function from. Because what is it that we notice? Depending on which x value we're looking at a specific piece of this function, right? So we have 3 different functions, and that's the idea. Once you get 2 or more functions that represent one big function, that's what a piecewise function is. So now remember, these domain values are important because these domain values are telling you that, look, for example, if x is negative 2, I can't use x cubed, because if x is negative 2, it's less than 0, I'd have to use x squared. Okay, so with that said, given this piecewise function, we're going to say evaluate g of negative 1, g of 1, and g of 2. Okay, so now to find g of negative 1, I have to say, look, my input is what? Negative 1. Which part of these restrictions does it land? Well, negative 1 is less than 0, which means I would have to use x squared. So g of negative 1 would be grabbing x squared, except I'm going to replace negative 1 in place of x, which gives me 1. Okay, so then what would g of 1 be? Well, g of 1 is not less than 0. It's actually between 0 and 2. So g of 1, when I'm plugging in 1 for x, I would use this. So g of 1 ends up just being the constant function, which is just 1. Okay, and then lastly, g of 2. Oh, and I forgot, and there's a mistake here, by the way. This should have greater than or equal to, right? Because that's what I meant to put it here. So if it's a g of 2, then what do I notice? This is saying if x is greater than or equal to 2, which means since it's equal to 2, we still use this, which is 2 cubed, and that's 8. Okay, so here's an example of a piecewise function in which we use to solve certain things, okay, or we use to evaluate. But remember, piecewise function, every time you hear of that, just think of it as a function that's broken up into multiple functions based on the domain restrictions. And notice how none of these domain values overlap. Even though this is saying less than 2, notice how it can't be equal to 2, right? So there is never an overlap in our domain values. Okay, now moving on to the next concept, which this is going to be a very, very important idea. This actually is a big deal in calculus as well. So we're going to work with the net change quite a bit. So this is defined as the amount the outputs change by from two specified input values. So in other words, if I'd say, hey, I'm going to give you a function, and I'm going to say, for example, from x equals 1 to 3, how much does its y value change by? Or on average, how much does it increase or decrease by? So that's the net change, right? So we're saying, look, how much does it change by when we go from 2x values and so on. So now, that is the function f of x has a net change of f of b minus f of a from x equals a to x equals b. So look at what this is saying. When we're trying to find the net change of a function from x equals a to x equals b, we want to know how much does the y value change by. So what is it that we do? We find out where we end up, we find a y value, and then we find out where we started off, we find that y value, and when we take the difference, we find out, hey, from a to b, my y value is changed by this much, whatever it is. So if let's say the number is 5, that would mean it changed by 5. It increased by 5 units, for example. Okay, so let's look at an example here where we'll kind of find the net change as well. So for example 3, we're going to say find the net change of f of x equals to rad x from 1 to 9. Okay, now remember, from 1 to 9, those are my x values. So what is it that I need to find first? I need to find f of 1, which would be what? That's my function. It'll be rad 1, and square root of 1 is 1. I need to find f of 9, and when I plug in 9, I get rad 9, and the square root of 9 is 3. So the net change from 1 to 9 would be, so the net change we know is f of 9 minus f of 1, where we ended minus where we started, which is 3 minus 1, and that's 2. So what are we saying? As our x values change from 1 to 9, my y value increased by 2 units. That's all we're doing, right? That's what the whole point of the net change is. Okay, so let's look at the next example. So for example 4. For f of x equals to 2x plus 3, evaluate a, f of a, b, f of a plus h, and c, f of a plus h minus f of a all over h, and where h does not equal to 0. Now, one comment I want to make here is that this right here, this last thing where we're going to get to, this is called the difference quotient. Okay, which this is a big deal in calculus. Okay, so I'm telling you right now, get used to seeing this quite a bit. This is kind of, if you were to tell me, hey, Mr. Gregorian, can you tell me something that kind of does a good job of summarizing calculus? This would be one of the things I would mention. Okay, so let's, before we get to that, let's actually do these pieces, because notice how f of a and f of a plus h show up there anyway. So hopefully you see why we're doing these two first, because to be able to do this, we need to do those first. Because look, how do I find f of a plus h? I first need to know what the function is. So let's go through the steps. Let's first focus on a and b. So what's f of a saying? F of a is saying, look, go to your function, and in place of x, now we're replacing it with a, which becomes 2a plus 3. And that's it. So we're done. I can't simplify this any further. Now 2a plus, so f of a plus h, what does that become? That becomes 2 times a plus h plus 3, because look at what I did here. This is saying go to your function f and replace the variable with a plus h, which notice how I replaced the variable with a plus h. Now this one I could simplify a little bit, which is 2a plus 2h plus 3. Okay, now here comes part C. Now part C, we're saying, look, find me f of a plus h minus f of a all over h. Now I'll give you a hint here. Whenever you're ever asked to find the difference or to work with the difference quotient, usually, most of the time, this h in the denominator should cancel out. So I would say simplify until you cancel out the denominator and the h. And once you cancel it out, then you've pretty much simplified it as much as you can. So here's the good news. This is saying, look, find f of a plus h, and then when you find it, subtract from it f of a, and then divide all of that by h. Which, if you notice in part A and B, I pretty much found f of a plus h, and I found f of a. So instead of doing all this work over again, I'm just going to recycle my work in part A and B. So this fraction here is saying what first? We need f of a plus h. And what do we say f of a plus h is? 2a plus 2h plus 3. So that will be 2a plus 2h plus 3. then we say minus. Now look, I always put parentheses around this because look, this minus belongs to the entire function. Minus f of a, and f of a is what? 2a plus 3 all over h. So if you look from here to here, what did I do? I just replaced f of a plus h and f of a with my function and what I did in parts a and b. Okay? So in other words, if we weren't asked to do parts a and b and we were asked to do part c first, guess what? We would have to do f of a plus h and f of a anyway to be able to go further. So just keep that in mind. Whether we were asked parts a and b or not, we're still going to have to do that. So let's simplify this now. So this becomes what? 2a plus 2h plus 3. Distribute the negative, that becomes minus 2a minus 3 all over h. Now look at how nice this is. A bunch of things cancel out, and that's not a coincidence, right? So the 2a's cancel out, and then the 3 minus 3's cancel out, and what am I left with? I'm just left with a 2h over h. And then the h's cancel out, and I'm left with 2. So notice how nice that is. So usually whenever you're asked to find this difference quotient, the h in the denominator should cancel out. So once you cancel out the denominator, then you've pretty much simplified it as much as you can. Okay, so let's now move on to our next idea, which this you pretty much already know. You have a good idea. We've already also mentioned it. So the domain of a function. So the domain of a function consists of the set of all inputs that produce an output for the function. Okay, so just keep in mind that if I have a function that we're asked to find a domain, if the input produces an output, then it's a part of the domain. If the input doesn't produce an output, or it gives us an undefined value, then obviously that input is not a part of our domain. So we want all inputs that produce an output. So we will find the domains of functions in different ways depending on the function. So one type is, so let's talk about two specific types of functions. One of them is, what if I have an even root function? So like these are my what? Square roots or fourth root and so on. Those, when we're finding the domain of this, one classic way is what? We just basically set the expression inside the root, inside that root, greater than or equal to 0, and solve. And when you solve that, then you'll know, then the second step would be the domain is literally the solution from 1, is the solution from step 1. And we'll write that in interval notation. And I trust that we are all familiar with interval notation. If you're not, ask me and I'll explain it to you. Okay, but that's the thing, because we know when we have even roots or square roots or fourth roots, we can't have negative inside the roots. So we say the easiest way to find a domain is take what's inside the root and set it greater than or equal to 0, and then solve for it that way. Now remember, if we have, by the way, odd root functions, odd roots, the domain is all real numbers. So the cube root of x, the domain is all reals. We can have odd value or negative values inside of odd roots. It's only the even roots where the negative values are a problem. Okay, so The second type is if we have rational functions, which these are functions in which we have a numerator and obviously a denominator. And we know that anytime my denominator is 0 of a rational function, that becomes an issue. So for rational functions, we're going to work the other way. We're going to say, hey, look, which x values make my denominator 0? Those x values that make my denominator 0 are not a part of the domain. So the domain will be all real numbers except for these values in the denominator that or these values in the domain that make the denominator 0. Okay, so the first step for this would be what? We grab the denominator and we set the denominator equal to 0 and we solve. And then the domain then becomes the set of all real numbers except for the values found in 1, if any. Sometimes we might not find any values from 1. So then the domain is the set of all real numbers except for the values found in 1. And then this is going to be in interval notation as well, in interval notation. Okay, so let's do our last example and then that'll wrap up the notes here. So for example 5, we're going to say find the domain of each function. Okay, so for a, f of x is 1 over x squared minus x. B is g of x is rad 9 minus x squared. And c, h of t is t over rad t plus 1. Okay, so let's look at the first one. The first one we could right away see it's a rational function, so I don't want my denominator to equal to 0. So I'm going to work backwards. I'm going to say, well, when does x squared minus x equal to 0? When that equals to 0, we know that those values are not in my domain. So we can solve this by factoring. So if I factor out an x, I get this, and what do I get? X equals to 0 or 1. So what's my domain? It's all real numbers except 0 and 1. So in interval notation, my domain would be negative infinity to 1. And remember, parentheses means it's not included. Or sorry, not 1. I should stop at 0 first. So it should be 0, union 0 to 1, and then union 1 to infinity. So this is the interval notation, which says everything except for 0 and 1. Okay, now going on to example or part B. This is a square root. So what do I want? I want 9 minus x squared to be what? Greater than or equal to 0. And now if you look at this, we have a quadratic, so we can solve this in multiple ways. We know that this factors to 3 minus x, 3 plus x, and I could make a sign chart for this. Now, because what do I want? I want to make sure that these products are what? Greater than 0. So one way of doing that is we want to know when is 3 minus x times 3 plus x greater than 0. So what I do is I take each factor and I'm going to make a sign chart for them. So where is 3 minus x equal to 0? It's equal to 0 at 3. Now when I move to the right of 3, like 4, 5, 6, and I plug them in there, those are going to give me negative numbers. When I move to the left, they're going to be positive numbers. So do you guys see what I'm doing here? I'm just making a sign chart for 3 minus x. When I move to the right, or when I'm greater than 3, is 3 minus x positive or negative, which is negative. When I go to the left, it's positive, right? Because if I plug in 2, I get 3 minus 2, which is 1, okay? So same thing here. What's 3 plus x? When is that equal to 0? At negative 3. Now, what happens if I move to the right? Like negative 2, negative 1, 0, 3 plus x is a positive number. And then when I go to the left, it's negative. Now, I make one final sign chart, which is, remember, I don't care about 3 minus x times 3 plus x individually. I care about them as a product. So 3 minus x times 3 plus x, I'm going to carry this negative 3 down and that 3 down. So remember, at negative 3 and 3, these guys are zeros. So what if I'm from negative infinity to negative 3? What do I know? 3 minus x times 3 plus x is what? 3 minus x is positive times 3 plus x is negative. Positive times negative is negative. And then from negative 3 to 3, in here, what do I have? Positive times positive, which is positive, and then from 3 and on, a negative times positive is negative. And remember, what is it that we want? We want greater than or equal to 0. So where is this greater than or equal to 0? From negative 3 to 3, which that's where it's positive. And I'm going to include negative 3 and 3 because at negative 3 and 3, this is equal to 0. So the domain is negative 3 to 3 with these brackets, and the brackets basically mean that it's included. Okay, so going over to this one, see, this is a combination of a rational function and a square root. Now look, because of the square root, what do I want? I want it to be greater than or equal to 0. But because of the rational function, I don't want this square root, the t plus 1, we don't want that to equal to 0. So this one, the approach we want to take is what? I want to take the square root approach and say, look, I want t plus 1 to be greater than 0. Not greater than or equal to 0, because when it's equal to 0, it's going to make my denominator 0. So this way, I'm removing that, and I'm solving for this. Now, if I solve for this inequality, I get t is greater than negative 1, which, what does that mean? My answer is from negative 1 to infinity in notation, in interval notation. Okay, so that's my answer. Right, so these are some examples we did where we found the domain of the function. You'll do plenty of that for homework as well. This wraps up the notes. So if you have any questions, make sure to ask me. Don't hesitate. You could email me, or you could ask me when we meet with the class. Okay.